Hi, my name is Jamal Ashraf, and we are starting the data structure, and then we are going to be using a Python for the example coding on the data structure that we are working with. So I'm going to share my screen, and then I'm going to get this one going. All right. So what we are talking about is about the searching algorithm, specifically for right now, it's going to be linear and binary search. Of course, the binary search, we can get to the recursion. I'm going to dedicate a section for that one, the recursion concept and the binary search coming up after this. So searching is something that we really need in computer science. We have certain data and we need to look for something, we need to find something. And then generally what we do is when we have a list of items, then we generally return the index of that item in the list. That item can be a number, it can be a name, it can be an object. Uh, so the key concept of searching for computer science is we got to have some algorithms, different ways of doing this. And then we are going to be using some kind of mathematical way of finding the efficiency of these things. We're going to be talking about big O. I'm going to briefly talk over here, then I explain it a little more. I don't know if I want to go through the detail of the big O, just the concept of it and how we're going to be using it. Of course, in the software engineering, we will have a more calculation of the whole code instead of a section of it. But here we are just focusing on the algorithm that we are using and if they are efficient and when should we use one over the other. So that's what we're going to be talking about, the efficiency of it, the optimization of the search that we're going to be doing. And that's especially if you have a huge data, that's going to be some concern to do it. And sometimes we sacrifice one for the other one. We want to spend a lot of time for a complex algorithm to find something versus an easy one. Our list is small, our list is large, and those are the things we're going to be talking about. So linear search basically is you start from the beginning of the list and you're going to check every single element till you find what you are looking for, or you run out of your list and then you just didn't find it. You can think about it if there is a line of people lining up for, I don't know, a concert or an event they're going to go in, and you're looking for somebody and you don't know that person. And then you go start from the beginning of the line and you're going to ask, are you this person? If it's a yes, you're done, you found who you're looking for. If not, you're going to go to the next one. If not, you're going to go to the next one. Potentially, you can go through the whole list and either you're going to find that person that you're looking for at the end of the list, or you basically say, I went through the whole list and I did not find the person that I was looking for. Now, there is something called time complexity. That's a mathematical way of finding how these things are related to each other. We're going to talk about it in conceptual way. I'm not going to go through detail of it. So when we're talking about the big O, we're going to find the worst scenario, worst case scenario, and then we're going to calculate how is that going to relate to the number of elements or number of visits we're going to be doing to the elements. So in this case, the worst case scenario for the linear search would be the whole list. So I have to go through the whole list. So best scenario is I'm going to find what I'm looking for on the first one. The worst scenario would be the last one. The average would be half of the list. I have to go through the half of the list to find something that I'm looking for. Generally, this is good for unsorted or small lists, so I don't have to worry about too much of efficiency on that one, and I don't have to write any complex algorithm, and I just go and find what I want linearly. So here is example of a code in Python, basically a function or a method that we're going to be using here. So we are using this function or method to find this target that we are looking for. And that's going to be the list that we are going to be using. So we're going to go through the whole list. The length of it is going to, so we remember when we say range, we start with 0, we stop 1 before this one. And now we're going to go through the whole list. We are looking for our target. If we find it, we're going to return the index of it. If we go through the whole list and we don't find it, we're going to return -1. The issue or the concern with Python is -1 can be an index. So you can use -1 as an index. It is not a wrong index. So some developers don't use -1, they return a text. I generally like to have numbers. So if I'm returning an index, I'm going to have a -1. And I double check it for -1 to be sure that's what it means. And I'm definitely going to document it in my software or in my function to be sure that people know this is going to return -1. Just want to get numbers. I don't have to worry about string versus numbers. So very simple, very easy to write, very easy to just do it. And that's what we're going to be doing with the linear search. The next one is called binary search. Binary search, the concept of the binary search, it says, okay, if we sort our list, which is going to be a cost for the binary search. Remember, everything we want to do, there's going to be a cost and it's going to be efficiency. So what is going to cost us to do this? The complexity of the code can be a cost because we have to spend more time on it. The how we're going to use this one is going to be a cost. So if we need to do any kind of a binary search, the list has to be sorted. Now, the cost is going to be what? We have to sort the list. So if I have a list that's going to be constantly removing element and inserting element, that's going to be the cost of this. So every time I insert something in the list, I have to be sure it's going to be inserted in a correct position. So the list is still sorted. Same thing goes if I delete an element, I have to move everything after that to be sure that my list is sorted. So if I have a sorted list, of course, the best scenario is going to be something that we are not going to be modifying too many times. So if we go to the concept of the binary search is we go to a list, we're going to look at the middle part, middle element. Then we ask the question, is the middle element is what I'm looking for? If that's the case, I'm done. If that's not the case, then we're going to check the value of the element that we have versus what we are looking for. And if it is small, we're going to start searching on the left part. If it's larger, we're going to be looking on the right side. And we're going to keep doing this till eventually we're going to find what we're looking for. The efficiency is big O log n, meaning that this is example over here. If I have 10,024 elements, it takes 10 comparison in the worst case because the 2 times 2 to the power of 10 is 1024. And remember, comparing this to linear, it could potentially, in the worst case scenario, take you 1,024 element visit to find what you're looking for in the linear. In here is going to be only 10 comparison. Excuse me. So that's what the binary search is. It's for the large, and it has to be sorted data set. So if you are looking for a word in a dictionary, we don't start from the first word and keep looking for it to find it. We're just going to go try to find something somewhere, and then we're going to go back and forth till we find what we're looking for. So we have an example in Python to do this binary search. Of course, there is two ways. There is a recursion way, and there is a iterative way to do it. We're going to go over the iterative. In the next portion, I'm going to be talking about the recursion and how we're going to use recursion to do the binary search, and for the future algorithms and how we're going to do those. So we starting with this code that is going to be for binary search. Again, this is just a method or a function to do that. So we are starting to set our, this is one way of doing, for those who might not be familiar with this. So we have two variable and we have two values. So these two values are going to be sitting in these two values. So this is the same as low equals 0, high equal length ARR minus 1. So that's called tuple. I hope that you guys covered it in the last class. If not, that's okay. So that's the way that Python can do this, with two values in two variables. All right, so after that, we're going to check for low being less than or equal high. So remember, the low is on the left side, high is on the right side, and we're going to keep moving them. And if they get past each other, that means we didn't find what we were looking for. Every time we start our process, we're going to take the low plus high, and we're going to do integer division by 2. Integer division meaning that we are not going to get any decimal point because we don't have no decimal index. So, for example, 7 divided by 3 is 2. 7 divided by 3 is 2. So we do that, and then we go to that particular elements in the list. We are checking to see if that's what we're looking for. If that's what we're looking for, we just return the index, we're done. If not, we're going to check the value of what we have in the list to see if it's going to be the less than target. Then we're going to move our low to pass by the mid. Remember, we know it's not the mid, so we are going to be moving our low to mid plus 1. That means our low so we're going to, our high is staying the same. The low is going to come mid plus 1. So we're going to be searching the right side of the list. If that was not the case, meaning that our value element is going to be greater than target, we're going to move our high to come before the mid. That would be giving us moving the high to the left, and now we're going to be searching the left side. So depending on the value, we're going to go to the left or we're going to go to the right, and we do the same process again. So let's go through this with the example to see how is it going to work. So we have this list. Let me move this one right here. So we're just going to start with a small list to kind of understand where we're going with. Our target is 7. So we're looking for 7. Remember, in the binary search, we are going to be cutting it in half. We're going to go left or right and look for it. In a linear search, we're just going to be searching. So if this was linear search, I would look at this one, look at this one, look at this one, look at this one. We would have 4 visits to find my target if it was linear. So that would be my target that I'm looking for. So I put that in a visual way. I put the index on the bottom of each element so we can see how we're going to trace this or go through this. Okay, so we're gonna keep track of the number of visits to see how many times do we visit this to get where we want to go. So first thing, we're gonna set our low and high to 0 and length -1. So my high is gonna be to the right, my low is gonna be to the left. My low is 0, my high is 10. Then we go to the target, which is 7. And then we're going to check to see if low is less than or equal high, which that the case is. Then we're going to calculate the mean. So maybe you should take a piece of paper or something to write on to kind of go along with me through this. Keep track of your low, keep track of your high, keep track of the mean, and basically check me to be sure I am doing it correctly and I'm not missing anything. So the mean is going to be low plus high divided by 2. So low is 0, high is 10. 10 plus 0 is 10 divided by 2 is going to give you 5. So my mean is going to be 5. Now, I'm going to check the element over here. That's 11. So we're checking to say, is 11 equals 7? No. So we're going to go to next one. Is 11 less than 7? No. So we go to the next one. So we're going to move high to mid -1. Remember, mid was 5. So we're going to move high from right to left. Now my high is over here. My low is here. Now we're going to go back up to the loop again. We're going to calculate our mid. So right now my low is 0. My high is 4. 4 plus 0 is 4. Divided by 2 is going to give me 2. So my mid is 2. Again, we're going to check it. Is this value what we're looking for? Is 5 what we're looking for? The answer is no. So we're going to go to the next one. Is the value that we are looking for, 5, is that less than my value that I'm looking for? 5 is less than 7. So we are going to be moving our low to mid +1. So my mid is 2, mid +1 is 3. So we're going to move our low to index 3. Okay. Now we're going to go back up again. Now we got to calculate the mid again. Now the high is 3, the low is 4. The low is 3, the high is 4. We're going to add them together. 4 plus 3 is 7. Divided by 2 is going to give me 3. So my mid is going to be 3, which is going to be exactly the same as my low. And so far we had 2 visits to our lists. Now we go back up again. We are checking to see if the value of our elements is the same as our target. The answer is yes. And then we're going to return the index of it, which is 3. Now, if this was not here, if we were looking for, let's say, 8 or something, then we had to go to another loop. In that case, so let's say I was looking for 8. So we would ask the question, is 7 less than 8? The code would be yes. Then my low would be going over to the right. And that's where we're going to stop. I'm going to return -1 because we couldn't find it. And when we visit this one, the number of visits were 3. Do you remember what was the number of linear search? That was 4. So even with the small list, the binary search is more efficient for this one. I mean, not necessarily it's going to be always like that, but for this one is going to be good. All right, let's compare these two together. So we have the time complexity, and that's what we calculate of each algorithm that we're going to be doing. So in the data structure, not only we're going to be talking about different algorithms, we're going to be talking about their efficiency and how is it related to the data set that we are using. So what do we need before we start? We need the list that to be sorted for binary search, and for linear search we don't have. So if I am doing this in a software engineering part, I have to calculate those costs for me for insertion, deletion, sort. First we have to sort it, then we have to do insertion and deletion, and estimate the number of those things and calculate what's the cost to keep a list of sorted data. Uh, so if I have 1 million items and this 1 million items are in my list, we're not talking about a database, we're talking about the list, and in average, we're going to be deleting and inserting 10,000 element every day, then we got to calculate those things to see if that's really help or not. So generally, the linear search is for good for the small data set. It's not sorted. Uh, so we basically want to put something together and just put it there. Uh, Maybe the efficiency is not that big a deal. We can wait for it. For the binary, we want to go to large data sets. Searching is sorted in arrays or list format. We're going to be talking more about arrays in Python. If you took the data science course, we talked about arrays over there. So if its efficiency is very crucial, we want to be using this binary search, especially with the large data volumes. So the best scenario would be the list is unsorted and list is small. And for the other one would be the B list is sorted. And when frequent searches are expected, making the initial sort worthwhile. So we sort the list and we do many searches. Worst case scenario for the linear search is if the element is at the end or it's not there. The worst scenario for binary search is the target element requires maximum number of comparison, which still comparing to linear search is good. So log 2 of n. So we can actually sit down and calculate these depending on the estimated number of elements we have in our data set. So performance on the large data set. For linear search, basically, it's not going to be very good. For binary search, is going to remain efficient. So we are talking about we have a data set and it's going to be growing. So we have some kind of a data and it's going to keep growing. And for linear search, is going to keep being less efficient as data set grows. For binary, it's going to stay the same. From the implementation complexity, the simple, straightforward, more complex, and we're going to be looking at recursive part of these two. So this would conclude our talk about linear search, basically searching linear search and binary search. We talked about that linear search operates by checking each element in the data set. The complexity is big O n, meaning that as the list grows, it's going to take more time to do it. There is no prerequisite. We can do it with any kind of a list. Again, it's going to be best for small data sets. For binary search, it has to have a sorted list, otherwise it's not going to work. The complexity is big O log n. So as we increase the number of elements, definitely the time is going to increase, but it's not going to be as fast as linear search. It has a more complex implementation. Might need some additional space when we're going to be talking about some recursive. We're going to spend some time on that one in the next talk. So we're going to talk about how recursive functions need more space in the memory and how they can potentially damage not damage, but basically run out of memory and crash the computer. We talk about those things as well. So in general, we talk about recursive being small coding, making a computer to do a lot of work behind the scenes. In some cases, like what we have here, we can use iterative instead of recursive, but we have some algorithm that it would not work except recursive. So we want to learn about recursive. We want to know how it's working, especially with the computer systems that we have these days, with the memories that we have. Maybe the concern of the memory would not be as high. But again, if we are not careful, we can potentially crash the computer. So which one do we want to use? It's depending on what we are doing and where we're going with that. Do I want to put something together right away and get it done with? Do I want to work on this for a while? What is the size of it? What size do we have? Do we have our data sorted or not sorted? Those are the some of the concerns that we're going to have to choose the right algorithm. And the frequency of the searches. How many searches are we going to have? How often do we do it on a sorted list versus unsorted list? Okay, so I'm going to conclude this one right here, right now, and then we're going to come up with the next one that is going to be on recursive.